Welcome to this video about the first order high-pass filters, resistor capacitor and resistor inductor. Here we have the circuit of a first order high-pass filter. We have the source signal at the input, and the first thing we meet is the capacitor. On the output pins, in parallel to the output pins, we have the resistor. So this is how the first order high-pass filter looks like. But how do we validate it when we see it and we perhaps cannot remember that this is how a first order high-pass filter looks like? The thing is, we use the DC infinite frequency approach. We assume that the input source has a DC signal, so the frequency is 0. How will the circuit act then? In case of a DC, the capacitor is an open circuit, so it will pass no signal through here, meaning there will run no current, and the output voltage would be 0 because we see ground through the resistor. So it's just 0 volt. So we actually here, down here at this point here, comparing V out over V in, we get 0 out. We have a big fat 0 up here, even though V in could be 1 volt. Then the next thing we do is to consider that V in have a frequency of infinite. Then the capacitor with an infinite frequency, we actually get here a very small value. So it's actually a short circuit. And then a lot of the current can pass through, and we actually get a voltage drop over the resistor. So in this case, V out equals V in, because we have a current flow and we can have a voltage buildup. In that case, here at infinite frequency, V out equals V in, and then we are up here at around 1 volt, not 1 volt, but 1 time, a magnitude of 1. So this is the approach we have to do to be sure that we are looking at the correct circuit. The next step is to find out the transfer function when we apply it as a two-port network. And the transfer function is the phasor output over phasor input. So let's see what the math is for that. We simply use the voltage divider principle. So what is the voltage over the resistor on the output? Since it's two impedances, we can use the voltage divider. So since we will take out over the resistor, it's on top of the voltage divider equation, and then the sum of the two components. And then we times it all with the input, the phasor input. And that's our output. As you may remember from the other videos, we want to have it here in the denominator. The equation should be J plus J something. So we have to beautify our voltage divider equation, also because the transfer function is V out over V in. Here we only have V out. So we take and move V in below V out, like here. So we have R divided by R plus the impedance of the capacitor. Now we divide each the denominator and the denominator by R, so we remove and it becomes 1 up here, and R jumps in here on this place because we divide by it. And now we have to get rid of this part here so that we don't have anything in the denominator as a fraction. Um, so we time in on all places with JF2PRC. So we get JF2PRC, and also here on the space with 1, JF2PRC plus 1. Then we have the definition of the break frequency, and break frequency can also be called the cutoff frequency, the minus 3 dB frequency, the half power frequency. A dear child has many names. As you can see, the break frequency is 1 over 2PRC, and we can actually see 2PRC up here, and we have 2PRC here. So putting that in as the break frequency, we get J over F and FB, the break frequency, into this equation. F is just moving up, and then we replace with FB, the 2PRC. So this is our transfer function for the high-pass filter. Comparing to the low-pass filter, at the low-pass filter we only had a 1 up here. But now for the high-pass filter, we actually have this complex value up here going in. This is the change to it. So in order to work further with it, now we have the transfer function. We also want to have an expression for the magnitude and the phase of this filter. So we use the transfer function equation and take the magnitude of it. And as you remember from complex numbers, we take the square of each. So here in this case, we take it squared and take the root of it up here, but since a square and a root cancel, then we have f over fb. Below here we take each value, the 1 is squared and the imaginary number is also squared, but since 1 squared is 1, we just have left frequency over the break frequency squared and then the root. This is our magnitude. For the phase, we have to remember we have a J up here. This is then causing that we have 90 degrees in the phase equation. But else we take minus tangents to the complex part of it here. So looking to how the magnitude and phase for the first order high pass transfer function look like, you can see that for low frequencies there's not much signal passing through, and that we also know from when we analyze the filter first with DC, that the capacitor has to open before there is actually an AC signal over the resistor. First, at a break frequency, our break frequency here at this point, there is actually 0.707 of, if we assume we had 1 volt here, over the resistor. This is the definition on our break frequency. That's also the same as 1 over square root of 2. So here at this point we have the break frequency. At the same time, the phase shift, when we put the break frequency up here 2, we get 1. Then we have minus 45 here. Then we actually get a phase shift of 45. For the low pass filter, we had minus 45. The difference between the filters is that due to the capacity here, we already have a phase shift of 90 degrees starting out with, and then the phase shift actually end up sometime at 0. But at the break frequency, we have 45 degrees. If we want to have the Bode plot, we need to get the magnitude in dB. So we take our magnitude equation and take the logarithm of everything and times 20. Applying the logarithmic like, math rules on this equation, we get 20 log to f over fb because it's on the top of the fraction, and then we get actually minus 20 log the square root of 1 plus fb. And since in logarithmic we can remove the square root by dividing by a half here, so this is then ending up at 20, going from 20 to 10 because we have times it with a half. That's the same as dividing by 2. So this is our equation for the Bode plot of the magnitude. And when we look to it, we can see for frequencies that are very low compared to the break frequency, we have an approximation in 20 log to f over fb. So it comes up from a very small number until we reach the breakpoint and the break frequency. On the other hand, for frequencies that are higher than the breakpoint frequency, we actually have 0 dB, meaning V in and V out is equal. So there's no change here. But drawing it as a Bode plot, it's until the breakpoint frequency, it's a square wave, it's a horizontal line, and up to the break frequency, it has a slope of plus 20 dB per decade, so it slopes upwards. If we look to the phase, how do we draw that in Bode plot? Well, at the break frequency, we know we have 45 degrees. It starts out with 9 degrees. So until we reach the a tenth of the break frequency, there's actually 90 degrees phase shift. From that point to FB divided by 10 to 10 times FB, we have a straight line through the point of where the break frequency is. And it hits 10 times FB. After 10 times FB, it's actually 0 degrees because the capacitor now is fully short circuit and it doesn't add to the phase shift. Oh, it's still next. This is the end of video 6. Thank you for watching.